So we're going to do an example involving a piecewise function. That's what you see here. Because these functions are, they don't always behave as nicely as, the functions we usually see, and they provide great examples regarding continuity and discontinuity. So this function g of x, it's equal to negative x or opposite x whenever x is negative, okay? If x is between 0 and 4, inclusive, then g of x takes on the value root x. And if x is greater than 4, then g of x is just equal to 3. The two questions we want to answer, first of all, for which values of x is g of x discontinuous? Okay, so that means that would be a value of x such that, g of x is defined near x, but there's a discontinuity at x. Or it's not continuous, I should say, at x. B, we just want to list the intervals on which g of x is continuous. Okay, so the first thing I'm going to do is I'm going to graph the function. So let's start with the first part of the interval. Okay, so here we have x is less than 0, or x is negative. So we're looking at values of x over here, okay, not including 0. And for those values, we are going to graph the function y equal negative x. And we know that that's just a line with slope -1 that passes through the origin. So I'm going to do a quick sketch. The arrow means the graph continues in that direction. And I'm going to leave an open circle here because we have strict inequality here. Next, I'm going to graph on the interval 0 to 4, inclusive, the closed interval 0 to 4. And so that's this interval right here, including 0, going all the way to 4. And we are going to graph the square root function. So we know the square root function, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, so I'm going to have a value here. And we know the graph looks sort of like this hook. Finally, I'm going to graph the third function of my piecewise function, and we will be graphing y equal 3, which is a horizontal line, on the interval 4 to infinity. Okay, so that will look like, so that interval is right here, it keeps going. And we will be graphing just this little segment, this segment of the horizontal line. And I forgot to mention here with the square root, we were graphing the function y equal root x. Okay, so 3 functions occurring on 3 different parts of the domain. So the domain here is all real numbers. So if you think about what I said in the last video, okay, if I was to try to graph this function or draw this function, I would start over here. And I would not have to lift my pencil until I get to 4. And then I would have to lift it up in order to draw the rest of the graph. So you can see instantly that the discontinuity. So the answer to part A is g of x is discontinuous at x equal 4. Okay, that's where there's a break in the graph. You can see that there's we call this a jump discontinuity because there's a jump in the graph. You might also have noticed that our function is continuous from the left. Okay. But I wanted to give a slightly more sort of technical answer as to why my function is discontinuous. So if we go back to the definition of continuity, remember that there were 3 conditions. The first condition was that the function had to be defined, okay, at the given value, so at 4. So notice that for this particular example, f of 4 is equal to 2. And so the function is defined. We don't have any problems there. The second condition that has to be true is the limit has to exist at 4. Okay, but if you take a look at this, if I look at the limit as x approaches 4 from the left of g of x, this is equal to the limit as x approaches 4 of root x, because that's the function, that's the piecewise function is defined by root x on that interval. So the piecewise function is defined by root x as I approach from the left. And this limit, using the limit law, is 2. And you can also just see that from looking at the graph, right? Now, if I look at the limit as x approaches 4 from the right of g of x, in this case, if we're approaching from the right, then this function takes over. And this is just the horizontal line. So this is just the limit as x approaches 4 from the right of 3. And the limit here is just 3. So instantly we see that 2 is not equal to 3. So the left-hand limit does not equal the right-hand limit. And this implies that the limit as x approaches 4 of g of x does not exist. And that implies not continuous. G is not continuous at x equal 4. Okay, and then we're pretty much, there's not, the condition 3 we can't even really talk about then. So hopefully I've convinced you that the function is not continuous at x equal 4. So let's go on and answer the second question. So the second question, part B, on what intervals is g of x continuous? Well, we can see that I never ever have to lift my pencil on this whole interval from negative infinity to 4. And then I had to lift my pencil and at the jump discontinuity, okay. However, I also want to add that at this value, the function is continuous from the right, or from the left, sorry, from the left. Okay, so I'm going to replace this actually with a closed bracket. Okay, because on this interval, the function is continuous from the left. And if you don't remember what that means, remember that it means the limit as x approaches 4 from the left, okay, is equal to g of 4. And both of these values we know are equal to 2. So this is 2 and this is 2. And the pattern you see is, if this was like a little tadpole and he was swimming, he would be swimming from the left toward the right.